print it out ahead of time, and by only posting like
No paper. We don't do paper anymore.
a moment before, I ruined that possibility. And yes, I do have a problem with the number of open tabs that I have.
It's not a
Wonderful.
problem. It's life.
Life is hard. Yes. Okay, great to see all of you. Well, let's give another minute or two for everyone to trickle in here. And my co-teachers reminded me that I was teaching out of the wrong slide deck last week. We had some kind of a duplication, so I didn't know that I was using the wrong ones. I hope I will not have done that today.
You're good.
Okay. But maybe we should get going. What do you guys think?
Yeah, start. Good. It's recorded for
late. Cool. Here we go. We are live and we're recording already. So what will we be doing today? So we'll first go through some admin issues. Then we'll very briefly at a super high level review what we did this week. And then we'll switch to the questions and answer period. I hope you all get to prepare. Oh yeah, and please everyone mute yourselves.
And if you make me the host, I can actually mute people.
Ah, yeah, wonderful. Here. Co-host. Oh, hold on.
Perfect, thanks.
Enable. And thanks to whoever asked to be for the transcripts. We should absolutely always have them on because as a foreigner from Germany, I know how hard it can be at times to understand people. But make sure you have your questions ready. And I should also say, how will we manage questions? I can't kind of simultaneously look at the slide deck and get your questions in a good way. So Anka will be monitoring your questions that are there and then ultimately prioritizing and scheduling them. The idea should be that questions that are similar, we should probably take them together. And I think that this making it interactive, giving you the chance to ask all your questions is, I think, very important. And it's something that I think we've been missing last year. So, and lastly, I'll give you a little bit of a preview of what's coming, not about exactly what's coming, but about what's coming, why it matters. So let's dive right into it and talk about some admin. So this is the slide that I screwed up and didn't show last time. We have lots of TAs, and I want to just express here my thankfulness to those. When it got clear that 522 was going to be a very big, a very popular course, we kind of panicked, and also it was unclear how we'd even do it, because if the groups are too big, then it's just like you don't have any meaningful learning experience. So I basically emailed lots of people and used all the networks, and we kind of said, look, if you don't volunteer as TAs, then there will be a very small course next year. And so I just wanted to say how thankful I am for them. And the TAs will be the primary people with which you'll be learning. So I think this is very, very important. Permits. Everyone should have gotten the permits. They should have been sent not today, but a while ago. If something is missing, email Anka. Everyone should have permits by now, or at least very quickly. And again, like the big wheels of the administration, they don't always spin very quickly, but they do spin. And like in the end, everyone who should have a permit will for sure have a permit, and we'll be making sure that that happens. Next, there was a lot of feedback we got on the Slack channel where people said, hey, we like, there's certain features of Piazza that we really like. Why not have both? And I should have added the why not both meme here, which I unfortunately forgot, but we will see what we can do. Now, UPenn is trying to move from Piazza to add discussion. And so we can't yet know if we should have Piazza or add discussion, but we'll see if we can set up one of those. It makes it easier to track tickets, But at the same time, we like pushing everyone a little into that Slack space, because a lot of companies are ultimately working off that, and a lot of teams are working out of that. Our robot is feeding our cats automatically, and apparently the robot is not quite in sync with the clock. In any case, yes, we are listening, and we'll see what we can do about that. To-dos this week. Anka, do you briefly want to talk about the to-dos of this week?
Yes, I can. Is the audio quality okay?
Yeah, you sound great.
Perfect. So first of all, pod start. You should have by now gotten your pod assignment. If not, reach out ASAP to me, please, and we'll figure out where you belong. Second, you will have 2 workbooks this week, and that will be the normal rhythm now. So each week you'll have 2 workbooks plus 1 homework. And we have week 2, day 1, and week 2, day 2 workbooks. They are up on the GitHub now, and they will cover basically deep linear networks, which is what Conrad introduces today as well. There will also be a homework this week, fairly short one, basically watching Coded Bias if you want to, and answering some questions on it. The questions can also be answered without watching the movie, but we encourage you to do so. The homework will be posted by tonight. I'm just making some final changes to it. Yes, and that's it for this week.
And let me just encourage all of you to watch Coded Bias. Why? A, you can watch it for free from your pen, but B, it's very easy to get there. There's just a link and all that. But far more importantly, it's easy to do theory of ethics of machine learning. Like, and the literature is full of like wonderful papers about it. But it's so easy to forget that there's people on the other side. And Coded Bias is, from my perspective, the best movie thematizing that there's really like, that the ethical dimension actually matters. And so I thought, and on top of it, it's a wonderful and cool and well done movie. And so I can only encourage everyone, watch it. It will be fun watching it, and it will help prime you for seeing it. And it's like one of these things that you can't unsee. Like if you once you start seeing how machine learning and deep learning do bad things to people, you start seeing it everywhere, and you will see it as part of projects and so forth. So highly recommend it. Now let's talk a little bit about this week's notebooks. So what did we see? So the first thing that I want you to realize is how easy you have it. So PyTorch gives you all those tools to construct these things. They are surprisingly new. So when I was starting there, and I know Lyle has been doing it much longer, but even when I was starting 20 years ago, none of these nice tools exist. So PyTorch gives us all these nice tools, how to construct networks, how to initialize networks, autograd, automatic differentiation. So you don't need to calculate derivatives, and thank God for that, because when I calculate derivatives, I always get the signs wrong, and there's like these horrible factors too in various places. In any case, when I do it by hand, I'm almost always slightly off. Autograd took that problem away. Easy routines for data loading and processing, easy routines for optimization. And as part of that first week's tutorial, these are basic functions, but as part of this first week tutorial, you get to use all of them, and or like a version of all of them. And you will also have seen kind of the gestalt that you have there. And so you saw how to make tensors, tensor operations, reshaping, permuting, concatenating tensors, interfacing with Python, basic data set loaders and transformations. All these methods you'll kind of be using in every project with deep learning that you'll ever have. I should also say some of you will be using some TensorFlow at a later point of time. It provides the absolutely equivalent language. So once you have one of them, it will be very, very easy to mix and match between different packages. So you also learned about a lot of the tools that we will use. You started using GPUs. GPUs make everything much faster. And you also started using Airtable and Colab, which are the methods that we use for teaching that allow us to make things interactive and get the information that we need from you and so forth. Now, what you also saw is how to build a fast little neural network. Not like you saw how to make it, you saw how to set up the training loop. And I think it's important that you saw this in the first week, because even the more complicated neural networks, they're all built in basically the same way. They might have more layers, and it might be different layers, and it might be recurrent, and all these things. But the basic workflow of building and using neural networks is basically always the same. And in that sense, it was nice that you saw it in this first week. So now it's time for the question and answer period. Let us spend a little bit of time talking about the questions that you may have about what we did during this first week in the notebooks. And I'll stop sharing the screen here so that I can actually see you. No. Okay, cool. Now I can see you. Great. Anke, can you
start? Conrad, before we do the worksheets, could you explain the difference between the worksheets and the homework for people?
Okay, so what's the difference? So the worksheets is basically a guided path through the content that is relevant for the relevant week. So this is basically a set of columns that will usually set up things, and then you edit a few lines where the actual magic happens if you want, although hopefully soon it won't feel like magic anymore. And then at the end you basically submit that through the quiz. Now the homework is basically a little freer, where we give you the questions, and you then solve those questions. Or Lyle, how would you describe
I would say that the worksheets are the classical learn the material, replacing a lot of lecture with learning stuff. And the homework is much more like a classic homework like you're used to in many, many courses. So the worksheets are much more tightly learn this, learn this, learn this, very micro-controlled, whereas the homework looks like a homework. And the worksheets need to be done before the pods, so you can actually talk about it and discuss it. Whereas the homework's a little more flexible. It's building on the ideas you learned in the worksheets.
Great. With respect to the questions, I see that we have a whole bunch of admin questions, and we have some content questions. Should we take the admin questions first, or what do you guys think?
I think we got most of the admin questions, actually.
I think the main admin comments are just that we're putting infrastructure to let people check their grades, and all that piece is coming. So bear with us a little bit, because the course is still in beta. And yes, we'll find ways for you to check to see, did your submissions go in correctly? Did you get credit for attendance at the pod? All that's being built. And hopefully, I'm hoping by next week, we'll have a full set of code that makes it all seamless.
And the nice thing about Airtable, Airtable kind of allows automation in that space, and we'll be trying to use it to maximum benefit there.
I think that was it mostly, unless Anke has other admin things, like we can move to content.
No, I don't have many more admin things. There's just like one thing about late policies, both for pods, making them up, homeworks, etc. I'll make a post later on Slack.
Cool. Great. So then what about content questions? Maybe we should move on to that.
We only had one in the chat, and it was answered.
Was already answered. Okay, well, I guess week one is special. We haven't done many truly interesting things, but we've rather introduced you to the toolkit that we'll be using throughout the course.
There was one question that's sort of fun to talk about. about the difference between subject-wise cross-validation and record-wise. Which I think is a nice, I see a lot of people in real projects getting this wrong. So I think it's well worth addressing.
Yes, and in fact, it's something that that we wrote a fun paper about. Let me find you the link.
But basically, always while he's doing that, it's a question of what does it mean to be out of sample? And the whole assumption behind out of sample is your IID, you're independently selecting samples. And if you have a whole bunch of, say, tweets from the same person, those are not independent. So to build a model that predicts for each tweet independently, is it a happy tweet or a sad tweet? You have this illusion that you know more than you do if you don't do out of sample by person. Because my tweets tend to have words like Lyle and Conrad or whatever. Yep.
Yeah, so let's break that down with more of an example. Imagine that Lyle always tweets sad tweets, like another rainy day, or like can't get out of bed today. And imagine that Conrad, it could be the other way around. This is just an example. And Conrad always tweets, hey, I'm so happy. I'm still so happy. What a wonderful day. Although, like, guys, I miss in person. So maybe it's the other way around. But this is something that in almost all domains is the case. Like, there are people who are just generally happy people in the way they talk, others that are generally not so happy people. Now, what that means is that if you know that a tweet is from Conrad, it might be more likely that this is a happy tweet, or it would be more likely than if it's from Lyle, because we have a lot of uncertainty on those things. So much so that if you guess Conrad is at his average and Lyle is at his average, you might be much better than if you actually use the words that you use. So if Conrad says, this is a horrible day, it might say 6 out of 10, Conrad's happy, because Conrad's usually happy. And so these subject fixed effects are huge. And what that means, and a machine learning system has no reason to not use subject specific effects if it can. So what that means is if we do record-wise cross-validation, let's be clear how that looks like. We get 10 tweets from Conrad and we get 10 tweets from Lyle. And what we do, if we do record-wise cross-validation, we take the 9 others from Conrad and the 10 from Lyle to predict the 10th one of Conrad. But in those 10 tweets, it's usually style. Personal style is very easy relative to, say, if I'm happy or sad, or even if I have Parkinson's disease or not. So it means that if we do record-wise cross-validation, we can there's 2 ways how we can be almost perfect. Either we're really good at figuring out who that person is, and we just guess their average, or we are really good at figuring out what the words mean. And so, but in practice, what we usually want to do is we want to say, well, now that we know how people feel based on what's in there, now let's take someone else, or do like William or Yi or Marcel, and say like, well, how do they feel today? So the real use case scenario is that we want to get out of that we want to deal with a new person. And therefore, the things that
that's the important point is, what's the problem you're solving? One problem is predict the happiness, sadness from future tweets for Lyle or Conrad, in which case record-wise is not unreasonable. But the use case usually is predict happiness, sadness from new tweets from new people. And if that's the use case, which is the one that I almost always have, then you need to say, I want to do out of sample by person. When you cross-validate, you need to hold out people, not hold out tweets.
Yeah. And I should say, it is a common mistake. So in that paper that I quoted you there, we did a survey of the literature, and half of the published papers just do it wrong. And that leads to them basically confidently saying we can diagnose Parkinson's disease based on the way you move through space or something. where all they can do is identify which person that is based on the way they move. Now, if you've ever seen skeletal tracking, if you see a video of a skeleton, of a skeletal tracking output, like walk through space, you're like, yeah, that's my friend John, like totally. Whereas diagnosing what disease someone has based on such data is really complicated. And that problem occurs in so many different domains.
Cool. There's a nice question on the XOR, which I think you could answer cleanly. Do you see it? If I don't.
Great, yeah, it's a nice question by Ryan, who says, could we discuss the y is f of x1 plus f of x2 minus of x1 plus x2 method for solving XOR? So let's think through that. No, so we effectively, what we have here, no, like this is effectively a two-layer neural network. No, I have an input, which is x1, x2. I have a mid layer here where I have f of x1 and f of x2 and of f of x1 plus x2. And on the output, I then have the output of the first plus the output of the second minus the output of the third. So this, what's described here by Ryan is a classical one hidden neural network, and we know that it can approximate anything. So let's see how that will work. So what we want is that the output will be 1 if they're different and 0 otherwise. I think there should be a, like if it's the same function, we're missing a parameter, we're missing a constant or something here. But like basically f of x1 could be something, it's only 1 if this is 1, otherwise it's 0. And then f of x2, same thing. And f of, in this third one, f of x1 plus x2, you can say only if both of them are on, it's big. Now, if there was a 2 before that last f, then we could make it, then it's clear how it would work. Basically, if both of them are 1, then we have 1 from the first one and 1 from the second minus 2, therefore it's 0. If both are 0, then, well, there's nothing in the first part and nothing in the second part. And if one is 1 and the other one is 0, and you have the parameter set just right for the last f, then it will basically, then the last part will be 0, and we will therefore have an output of 1.
So, Conrad, that's a little bit hard to follow when it's just said. And if you have a, and Joran, could you audio mute? Thanks. Conrad, if you have either a display device, an iPad, or I just use a camera.
Okay.
Something you can scribble equation.
Your co-host, feel free to hold something.
Okay, I will go plug in my device and for the future ones, write things down.
But you can use a piece of paper, maybe.
Yes, I have a piece of paper, but I also have a clever actual camera that we can use to screen share with. But yeah, go ahead.
It's getting high tech here.
Yeah. We get high tech. Cool. But in the meantime, go ahead and take other questions. I think for the future, we will do whiteboarding is an excellent suggestion.
So Yushan Wang says, let x1, x2 be binary, let f and f be the identity function. If it's the identity function, then this is not a solvable problem, no? No, because then all we do is we just still have a linear. We just have linear functions of the input, and if you give me linear functions applied to linear functions, I'm still in linear space, and there is no linear solution to XOR. Lyle, you were gonna share your camera?
I'm still setting up. I take some time to go find it and get things there. I wasn't ready, so we'll do this for future ones.
Yes, Yushan, that is totally a solution that you have. Now, like, does everyone see how Yushan's solution works? No, so basically, f is the identity function. So if x1 is 1, then f of x1 is 1, otherwise it's 0. Same thing for f of x2. And now g is the heavy side function. So basically, g is, but hold on, I think it needs to be 2 times. You should to be right, no? No, so g is only, g basically will only be 1 if x1 and x2 are both 1. And in that case, if we have a 2, if g is 2 times if g is 2 times in 2 in that case, we basically have 1, 0 goes to f of x1 is 1, f of x2 is 0, g is 0. 0, 1, f of x2 is 1, and g is still 0, and f of x1 is still 0. And if they're both 0, then both f and g are also 0. So it's correct. And then if they're both 1, we have 1 plus 1 minus 2, it's 0. So in that sense, yes, it's a solution. And Lyle, you have a graphical version of that.
Let's see if we can try our technology here. Let's see. Oh, I'm having troubles. The answer is let's see about that. So we want something. Do people see screen share?
Yeah, it's great.
We love technology. Look at pencil and paper in the Zoom era. Right. So we want something that if you have sort of x1, x2, and then I guess we have to decide if they're 0, 1 or plus 1 minus 1. But let's just do 0, 1. We've got sort of 4 options. We'd like to have these two be together. That says that they're equal. And these two be together. That says that they're not equal. So you want some way there's no hyperplane to separate these. But we could instead say, can we do some sort of a nonlinear function? And there's several ways to do it. There's a bunch of them. One could do products. One could do a heavy side function, which a heavy side function says you go, well, in this case, heavy side is going to have to be at 1. But if you have x1 plus x2, and then you could have some threshold that says that 0, okay, in this case, it's 0 if they're both 0, and it's 1 if either one of them is not 0. That makes sense? So the heaviside function already sort of says, hey, check to see if they're both non-zero. So I'm not sure if this is helpful or not, but I think the key point says that in a space where you want to have 2 points here and these 2 points be separate, there's no hyperplane to separate them. But if you take something which is some of them or some product of them, some product of them or some nonlinear function of their sum, then in that new space, if you take, say, the sum and the difference or a bunch of different pieces, you can then end up having something that is separable. Conrad, how should I say that better? Or maybe just move on.
I just wanted to make sure that everyone sees the link to neural networks here.
Yes.
So if you look at my video here, this is the neural network that Yushan's solution implies. I have 2 inputs, x1 and x2. On the second layer, I have f of x1, f of x2, g of x1 and x2, where f is the identity function on both sides. G is the heaviside function. It's basically it's x if x is greater than 0, and otherwise it's the same. And then we have like a weight of -2 here and weights of +1 from both sides. And that function is one implementation of the XOR function. There are countless others. Like we basically just test that function with 4 inputs and 4 outputs that they need to have. So there's an infinite set of functions that can implement that. Great. Any other questions? Hold on here. Jackson Golden asked, isn't it the case that any network that does not contain nonlinear activation functions is essentially linear, regardless of depth, size of hidden layers? Yes. As long as everything is linear, it will always be linear.
Any linear combination of linear functions is still linear.
I should say there is a fun exception, and I don't think we'll have it in the course this year, but you can actually, if you use, not like our multiplications, they run on an actual graphics card. And an actual graphics card, the output isn't exactly linear in the inputs. Not like, you know, there's bits, and it turns out that there's a slight nonlinearity around 0, where +1, basically, there's a whole range that gets pushed towards 0. So it turns out that if you give it the right initialization, you can train a linear neural network using PyTorch to actually solve the XOR problem, because the graphics card makes small mistakes in the vicinity of 0. And yes, you basically need to use weights of 10 to the 23, and you need, but the result is
it's not linear anymore.
Okay, but the reason why I just mentioned that is that you will find that a good number of failure modes of deep learning happen because our abstraction of what happens in deep learning isn't exactly what happens in the actual hardware implementation of what we have.
We actually do have that, I think this week actually, in the workbook.
Oh, wonderful. Okay, cool. Then you get to see it, and it's actually great fun. Great. Do we have other questions here that we should take? Yes. So Wesley gave the answer to that. Now, like if you have a multi-layer linear network, you can say every layer is characterized by a weight matrix, but that means that the set of all layers is just characterized by the product of all the weight matrices. Ahmed asks, so the solution to XOR requires at least 3 hidden units. Is that correct? That can't quite be correct.
It's not correct.
It depends on the nonlinearities that we put in. Yeah, I believe, for example, that you don't need to. Yeah, you can suddenly make the third one go away. In fact, you can make all but one go away if you allow the right kind of nonlinearity in the first layer.
Like make an XOR as a nonlinearity. Hey, we can build that in too. We don't have to do a ReLU or a sigmoid. We can put any function we want in. Let's build some XORs in for our networks.
In fact, I should mention here, some of the research that my lab does is that we ask if you have real neurons in real brains, what is that input-output function of these neurons? And it turns out that real neurons in your brain can do XOR. My friend Matthew Larkham from Bern did that experiment after I like really told him that deep learning people would be interested in it, and had a nice Nature paper that showed that neurons, I believe in human brains, can calculate the XOR function by a single neuron. And the way that it goes is because if you have multiple inputs coming into a real neuron, you have these things called NMDA spikes, which are locally and very super linear in the dendrite. And they also have inhibitory inputs. So it just requires a small number of biophysical primitives to do an XOR in a real neuron. Great. Any more questions? Well, if there's no more questions, we should probably keep going. But I want to encourage all of you to look for good fun questions. So you will, some of the things you will learn by like the notebooks will be really good at teaching you the mechanics of doing deep learning. I hope that the principles that we bring across as part of them will also help you see the big picture of being an engineer in that space. But much of kind of like the real learning experiences are really by asking non-standard questions, kind of asking weird things, playing with the ideas. And in that sense, I think that this making it interactive is really going to be useful for all of you. So please, for next time, try and brainstorm fun ideas, questions you'd like to ask. And that can be very wide-ranging. What you can use it for, what you just learned, aspects of the learning that you were missing, and kind of the broader context of ideas of things.
We will collect feedback from you and figure out how to do this better. It's also the case that the other weeks will be more difficult, more confusing, interesting concepts. We'll also try and include some pointers to some of the more current literature, right? This is really pretty much background history stuff. We'll be getting into some of the places where there actually is lots of argument in the contemporary deep learning literature. And there certainly, if nothing else, the TAs and you and I can ask each other questions about, is that really true? Is that always true? Really, couldn't we do it this way instead?
And I want to say one more thing that I think is very important. Lila and Anka, I want to encourage you to butt into what I say at all times to kind of give more background.
I'm way too shy to do that. I never interrupt you.
Correct me when I say wrong things.
We will, but you don't.
Great. Cool. So why don't we go back to the presentation help here?
So maybe one more thing on feedback that will count towards your participation grade, because we didn't receive many of them. We didn't announce that. I'm sorry for that. I forgot to put that on the slides last time. But your feedback is super important to us. So that's why it's part of the worksheet. So please submit that from next week onwards.
And again, key point, it will be on the worksheet.
Yes.
Great. So we will have plenty of time for the remaining slides for today. So all the more reason for Lyle to provide a little bit of extra color for them. So today we will, in this week here, we will talk about linear deep learning. Now that seems weird. Now, like we just had that question, like, can we just multiply or does it make sense to have multiple linear layers? Like, no, it doesn't make any sense because multiple linear layers is just one linear layer. It turns out that learning in linear deep neural networks is a great way of getting an intuition on what on earth is happening in these things. And the cool thing about linear networks is that we can understand a lot about them. Not like it's a bunch of matrices that are being multiplied. We understand a lot about what happens when you multiply matrices with one another, which means that in the case of deep linear networks, we can really have an intuition on what happens during learning. And that is so important. And I'll try to convince you why it's so important in the next couple of slides. And we'll look at linear networks that are shallow, and we'll look at linear networks that are deep. And these basic mechanisms that characterize linear learning, they are present everywhere in the nonlinear learning as well. And you'll see about that. So let's skip through that. So let's talk about the bad way of thinking about neural networks. Or like, actually, it's a good way of thinking about neural networks. It's just really sad. So you can say, how does neural network progress as a field? Can say, we look at, say, the literature of 2012, there were a couple of papers, a few papers using Tange, a paper maybe using Huilu, a couple of papers that used various tricks. Keep in mind, 2012 is pre-AlexNet. AlexNet is what repopularized the field of neural networks. And then in 2013, what did the new papers that people wrote in that year do? Well, they looked at the papers in 2012. Some people were very inspired. Some papers were very inspiring to people. So the idea now is used by multiple papers. Some people were less inspiring. And so some papers had real influence from 2012 to 2013. And some of them had less impact. And we see that same thing from 2013 to 2014. Now, and maybe in that year, we had the first paper that really made something deep and that succeeded at making things deep. And then because it succeeded at that, it started inspiring more and more papers. And so in that view, it's an evolutionary view about deep learning, where you can say, what is a paper? Well, a paper, there's arguably two papers. There's papers that take two very different papers and merge them together into one paper. It's like reproduction in biology. And then there's other papers that take one paper and make one little aspect of it better. In deep learning, that might be a small number of lines. And like all these tricks that we will be learning are just a few lines of PyTorch code. Not like you want to do dropout. There's like literally one line of code. Of course, in parts, it's because PyTorch made it easy to do dropout. But in general, there exist these two kinds of things, and the two types of papers. There exist the kinds of papers that say, I have this cool idea from maybe text processing and that other cool idea from computer vision. Let's bring them together and build something that does both. And there also totally exist the papers like, here's a paper doing this thing, it's cool, and let me improve this aspect of initialization of the weight matrix. And both kinds of papers you find prominently published in all kinds of venues. I should say we will talk extensively about AlexNet, which would be a 2014 paper, if I remember that right, as part of the vision sequence. So you'll get to see it. But needless to say, pre-AlexNet, artificial neural networks were super uncool. I was in the field. I could never publish papers on neural networks because everyone was like, that stuff is so old and useless. And then all of a sudden in 2014, AlexNet massively won competitions and everyone dropped whatever they were doing and started doing neural networks. So the recent history here has completely changed in that interval. Now, this is a very sad way of thinking about it. Now, let's first see what it is, what these ideas are. Now, like I used a small number of them here, like ResNets, ReLU, Tench. You'll see all of these in the next couple of weeks. But there's not just those, but there's this huge set of tricks that characterize deep learning. Now you can say, here's it's a web page that I can highly recommend to everyone. Papers with code. You basically have all methods, all papers that are important at all implemented. What do we have here? We have like 84 methods that are associated with attention, 56 stochastic optimization techniques, 50 regularization techniques, 47 attention mechanisms, 46 activation functions. We'll talk about all of these. But the important, and similarly, you have specialized things for the computer vision literature. Now you can see these are little tricks. They aren't big engineering insights. They're just little tricks how you do something and it works well. And a malicious view is just like what you have to do is like figure out which combination of them is right. And in that sense, you can say it's a neural networks isn't engineering, it's really evolution. What you do in practice, and a lot of people work like that. In particular, people who never took courses in that area, what they do, you want to solve a new computer vision task, you download the paper that did the most similar thing to that, and then you try and like do small changes that hopefully improve something. And in a way, that way of thinking is certainly part of what's going on in neural networks. And I think we need as a community to go beyond that. But it's at the same time, it's remarkably effective. And I want to highlight that, why evolution is so effective. And this is a wonderful book by one of the pioneers of the deep learning field that I want all of you to know about, which is David McKay, who did a lot about the merging of Bayesian ideas with neural networks. And in his book, that is still, from my perspective, the best book on information theory, he asks how much information do we accumulate about evolution? And you could say there's a naive answer to that. Now, like we've been humans for maybe 4 million years, give or take a little bit. How much information can you accumulate for it? Well, you can say in a way it would be 1 bit per generation that we'd accumulate. And I think that vastly underappreciated. So, but keep in mind that means that even if this was the case, which is a really bad model for how evolution works, even then we could have accumulated 400,000 bits about which neural networks makes us thrive and which ones don't. Which means that we might want to expect that that what happens in our head is somewhat complicated. That basically the algorithm used by real intelligences is a complex algorithm. Now, is that 1 bit per generation right? Well, under certain assumptions it is. So David McKay sets up the simplest evolution model that's possible. What we have up there, the fitness here, f of x, is 1 over n, where n is the number of bits that he has a binary. He has a binary genome here. It's 1 over n times the sum of all the bits, and that's and you randomly initialize that. Now you basically try out every possible you can try out every possible combination. Now that means that we have a smooth landscape. Now, like for every bit, it's either good or it's not good, and then we can over time randomize things and see how the system gets to be good. And let's see. One way of thinking about evolution is the mutations and view, where what happens? I randomly flip some of the bits, and early on, I might want to flip a lot of the bits because we're very suboptimal. So we randomly flip some bits, and then the better half survives. And how long does that take? So now, at first, we want to flip a lot of them. And then as time goes on, we want to flip fewer and fewer of them. And it turns out that this takes 2 n time steps. So do you have an intuition on why you want to have a high mutation rate early on and a low mutation rate late?
Okay, we have a winner in the chat window.
We have a winner
early exploration.
Yes. So early on, half of the bits are right and half of the bits are wrong. So you want to flip an awful lot of bits so that you get more of the chance to get them right. Because basically you want to have high variance, because you will basically lose the lower half of your distribution. So you want to have high variance. No, you will have approximately, you will have a Gaussian distribution of fitness when you start. If I give you the chance to cut away half of that, then now the mean is going to be like standard deviation over square root of 2 or something like that. So, so early on, high variance is good. You want to flip basically a good proportion of all bits. Late, that's a very bad idea, because of the bits, the majority will already be right. So every mutation that you make makes you actually worse. And there's a part that's related to the mean, where you want to have small one because you're better than average. And there's a part relating to the variance, and they go into the opposite direction. So early on, you want to have high rate, late you want to have small rate. Now, it means that if you have a genome of length n, you would need to take 2 n generations. Now, humans have 10 to the 9 bits roughly on their genome. So it would take 10 to the 9 generations to get there. Now, there's another model that he highlights in his paper, which is the crossover model. Now, like the mutation model works like this, that basically you only have k if k is the number of generations, parents. As everyone has 2 mutations, and then you take the beta, and you have again 2 mutations, you take the beta, and so on and so forth. So the number of parents that they have is linear. Now take the other extreme model that is much more like biology. You take all the bits, and no, you have a large population that all do that in parallel. And where instead of randomly flipping bits, what they do is they take 2 of the beings, and then they take half of the bits of one and half of the bits of the other. And it turns out that that's much better. So instead of taking n generations, we just need square root of n generations in this case, with like a prefactor that is fun because you can actually analytically solve for it. And in this case, you don't even need mutations. You can say you start with an arbitrarily large population. But why is this much faster? Well, because you basically accumulate bits over time. How many parents do you have, or like how many ancestors do you have if you go k steps into the past in the crossover model? How many ancestors do you have if you go k steps into your own family tree?
Yes, everyone's got it. 2 to the k.
2 to the k, exactly. Now, of course, they will start overlapping in reality if we look at biology. Now, that same idea is also true, of course, for neural networks. Like there's some ideas that work well. And in a way, it works much better than evolution. It's not that they randomly combine things, but I like, look, this is a good idea. Let's try like transformers with layer-wise normalization or something. Like, sure, we can combine these ideas, and there's ideas that are behind it. But like what I wanted to say with this is just, if you have a large population, evolution can be very fast. So even if we have no idea how deep learning works, if we're just like monkeys typing in extra lines, running our PyTorch code and like retaining the lines that were helpful, we will be not so slow. And in fact, there is a Google DeepMind paper that's called, what's it called? Alpha. It's not called Alpha Zero, but it's something zero. It's called Gradient Zero or something. If someone has the link to that. So in any case, it's completely random. It basically, there's no neural network simulator, basically just jumbles lines, and it's surprisingly not so bad at things. So in any case, what this just means is that we might be much faster by being entirely clueless than we believe how fast we'd be if we are entirely clueless. And it gets worse. So here's a wonderful book that I read. It's called The Plausibility of Life by Kirschner and Gerhardt. And it is a book about the ancient history in biology. And it basically asks the questions. We're in this world where we have all these animals with legs and arms and brains and all that. Can we have come up here through the processes that are in evolution? It seems that we have billions of free parameters in the construction of our brains. We could never search through this billion-dimensional space meaningfully because there's an exponential set of solutions. But what the book focuses on are basically 4 ideas. The first one is constraints, deconstraints, development, and weak regulation. And I want to briefly bring it down for what these evolutionary theory things mean about in the context of deep learning. So what did I learn from reading this book? So the first thing is, of course, learning is hard when we have really ugly landscapes. So if in the Mackay case, we had a very simple landscape. Now, everything was linear, with a linear sum of bits. It's very, very fast to learn that. But if we're in a space that is arbitrarily complicated, it basically takes forever to converge. And one of the things that make convergence hard is constraints. Let me give you an example from biology here. So let's say we're in this 2-dimensional space. Imagine our phenome space is the same thing as the genome space of body size, and we have heart size. If your body's really big, your heart's really small, you're in trouble. You don't have enough power. If your heart's really big and your body is really small, you waste lots of energy. You're kind of not very viable. So the idea is that this blue ellipse here characterizes the fitness function that you have. And you have a starting point here. And you can say, what does genetic change do? We basically have random movements relative to that. And we will later see what development does. So we start at some point. There's a certain ideal point, and you can say evolution is basically try and get towards that ideal point based on where you start. But if we have constraints, we have the following problem, that most changes that we could make will strongly lower our fitness. And like, I want to try like as a random change here. Oh my God, here now the body is, the heart is too big. I do another random change, now the heart is too small. So if we have such constraints, evolution will just run slowly. Now, let's talk about deconstraints. So the idea is that then what evolution would do in that book is to replace, to do a reparameterization so that we can't really be wrong, or like that our search space is aligned with the real space. And we see a lot of these examples in deep learning. So in many cases, we have this problem that we need to choose the batch size. How many data points do we put in at the same time versus the learning rate? And if you specify them independently, if one is too big, the other one's going to be too small and vice versa. And that made the field really slow in that area. But it turns out that we later on found that if we keep the ratio of learning rate to batch size constant, then learning will generally be good. So it's a reparameterization. If we look at it from this developmental perspective, we can say we have the body size and then we have the relative heart size. And by going through this space, we can all of a sudden accept the vast majority of our random changes that we do. So we basically align the search algorithm that we have to what's going on. And this is something that we've often done in the course of deep learning. There's another possibility.
I think it's worth noting, to tie this back to things people will see, that when we do gradient descent, because we mostly don't do the randomized search because it's sort of painfully slow, we will also see that, for example, rescaling the features, normalizing the features, has exactly this same sort of structure, right? So there are a number of ways to do this, of which the dumbest is you have a world that has these narrow ellipses where it's hard to do search. You rescale things to make them be more spherical, where the search becomes much better. So there are a number of transformations, of which just standardizing the input features is by far the easiest, that make the search space easier. And no matter whether you're doing randomized search or my more favorite gradient descent search, you still want to think about the shape of the search space. That makes sense, Conrad?
Yes. But Lyle just reminded me of something that is super important. When you do deep learning, there are always two levels of optimization happening. There is what's in your neural network. And in your neural network, you do gradient descent and optimize the parameters. But then there's you. And you are an optimizer. It's just like you're never aware of that. No one ever tells you that. What do I mean with that? You have some code that sets up a neural network. That code defines how good the network will be after it's done gradient descent. This setting up the code means that your effect, and of course, if your neural network works well, then like your employer will be delighted, or you'll write lots of successful conference papers or so. So you want to optimize both the inner loop of where the neural network optimizes, but also the outer loop where you yourself are an optimizer. And that's the only thing that you do, in a way, apart from ethics. No, but like there is this central component where you are the optimizer. And the question is, how do you operate as an optimizer? And you're not doing gradient descent because no one, but what you do is you like run your neural network and you're like, shoot, like it never, like the weights never changed. Let's increase the the rate at which the neural network learns. And so you do all those things to like optimize your network, but like thereby you're an optimizer. And therefore, like starting to be aware of the nature of you being an optimizer is super important. And there's two ways how you can be a very, very different optimizer. You can either really understand how neural networks work, and therefore, you can be very targeted. It's not that you just try stuff and it works or it doesn't work. Or alternatively, you can try stuff and it works or it doesn't work. Both of these modes are successful at times. And I want you to think about this process of you being the optimizer before you actually being the optimizer. Okay, because and why? Because it gives you the reason why you want to bear through all that theory. Like, why do you care about theory? Maybe most of you never want to be theoretical deep learning scientists. Well, the reason why you do is because you want to be better than like basically someone randomly changing their code. Keeping well in mind that randomly changing your code is actually a pretty decent strategy.
Well, it's painfully slow.
But it's
I know
arguably
you think square root of n is fast, but n is big, so square root of n is still a very big number.
It is absolutely, yes. Okay, so but let's get back to the previous part. So we again have a fitness landscape. Now, fitness landscape just means how good is the neural network on the benchmark that you want to have, if you want. And we had that first place where like changes usually get rejected because like if you do the change, they're out of whack relative to one another. Now, the idea of development is a powerful way of solving this problem. And you see it everywhere in biology, if any of you are ever interested in biology, which is instead of specifying those two parameters, you make it that one parameter is basically the parameter on which you do evolution on the x-axis here. And then you have a developmental routine that makes it that all the rest are just automatically set to the correct value. So you see that here we have the random perturbations in red, and then we have this green developmental process that immediately fixes it. And that idea, weird as it seems, is deeply at the basis of deep learning. So in the past, when I started deep learning, people were mostly not doing gradient descent. They had they specified a network and they specified the learning rules. And if the two of them were just perfectly matched, it worked. Great. And most of the time it didn't work. Gradient descent takes this thing and makes it always work. It always optimizes the right function. So gradient descent already basically took an awful lot of things that we did coding ourselves and made them into something that is development. Basically, I specify that, and then gradient descent helps me specify all the rest. The second one is for a long time. Then later, we specified the network and the gradient. If you did a mistake on the gradient side, your algorithm wasn't going to work properly. And autograd takes these things that needed to be in sync. Now, it needed to be that your gradient calculation is right, and takes it off your hand. It's just automatically right. We used to have lots of dependent parameters where you say, oh, but if I make this weight vector a little longer, what's going to happen? Well, then I need to learn slower because otherwise it doesn't work properly. Today, we do a lot of these things by hyperparameter optimizers, a topic that we'll cover in week 5, I think. And again, instead of you specifying things, you specify only certain things, and then the system basically specifies all the others. So hyperparameter optimizers are really equivalent to that. Now, keep in mind, this doesn't take away that it's like still kind of evolution, but like the whole notion of the whole notion of development here makes it that the set of things in which you need to innovate gets to be smaller and smaller. And then you can focus on innovating maybe in more interesting ways. In any case, I also want to say that evolution does stupid things. And like we are all born with an appendix. It's entirely useless at the moment, but cutting it out is just not something that biology is very good at. The field of deep learning, without any doubt, has all kinds of really, really bad ideas that people are just following up on because others used it before. And here's a great paper of that I very much recommend to anyone interested. Machine learning systems are stuck in a rut, a paper by Baham and Isad, both of Google Brain. What they did is they looked at hand optimization of code. Now, like you have two neural networks. One of them is very standard, the kinds of stuff that like everyone downloads and runs, and another part that is very non-standard. And they by hand optimized it. And what they find, we explain how the evolution of hardware accelerators favors compiler backends that hyper-optimize large monolithic kernels, show how this reliance on high performance but inflexible kernels reinforces the dominant style of programming model, and argue these programming abstractions lack expressiveness, maintainability, and modularity, all of which hinder research progress. So what has happened already is that the optimizers and the things that I write in deep learning are optimized for one another in the same way as pieces of our body are optimized for one another, which means that I can no longer even innovate because my new innovative non-standard neural network will run factor 100 slower because the guys writing the compilers have optimized for the code that everyone else writes. So the downsides of evolution, that we no longer understand things because they're all co-evolved with one another, is starting to show up in the field. It gets to be harder and harder to actually do innovative things, not because they don't work, but because everything's been optimized to make these things, the things work that everyone else does.
Well, let's be super concrete about this. There's a question of things that don't fit well in PyTorch are hard to do. Things in PyTorch that don't fit well on standard GPUs or tensor processing units don't work well. There are a small number, this has been true for all of science, that there is this coevolution of the hardware. Are your chips being optimizing vector processing, or are they going to do something that's asynchronous with other pieces? And so the science of, say, asynchronous updates versus vector pipelines, everything goes together. And it's necessarily, and for that matter, silicon versus gallium arsenide. There's a lock in to the things that you're good at doing. So it is the case that it is hard to shift radically different architectures because they require PyTorch, vector processing, different optimization strategies, different hardware, all the way down the pipeline. But that's life.
That is life, but it is parts of life that we need to be aware of. And it's a puzzle for a lot of people. Why is it that neuroscientists contribute so much to the history of deep learning? This might explain one of them. The fitness function that if you're on the applied side that you're optimizing for is primarily how good you're on the benchmarks. But that doesn't allow you to say, well, but hold on, this is just not right. It just works. But like, it logically makes no sense. Let's not do that. Whereas neuroscientists are given the freedom to basically build codes because they think they're right, and then they argue that the brain does it, even if the brain doesn't do it. And therefore, weirdly, this protection had the effect that, in my view, that many of the leading contributors to neural networks are actually neuroscientists. Arguably exactly because they are allowed to tinker with things before they become the dominant paradigm.
Or perhaps because they have different ideas of things that work, like local receptor fields or modules or a bunch of examples of what happens in biology. I mean, let's be clear, it's still the case that the most successful neural nets are wetware rather than hardware. And yeah, we're catching up with the hardware, but it ain't anywhere near the wetware yet. So there's still some inspiration there.
Yeah, and it's unclear if we're catching up with the hardware. Like doing the accounting is very, very difficult. Now, the brain has 10 to the 15 synapses, arguably running only at 1 heart. So is it that the brain has 10 to the 15 floating point operations? well, it might have much more, it might have much less. So I'm not giving up on human hardware yet. Cool, but let's briefly zoom out from there. Now, the view of like deep learning is an evolutionary field is undoubtedly correct, but it's just set, and it's obviously not everything. And I hope that you will contribute to making deep learning applications less random. And so let's talk briefly about what I love about week 2. Like, this is all just zooming out from week 2. Week 2 focuses on deep linear learning. In that domain, we really understand things, and we can have beautiful theories that let us see what works and how and why and so forth. In a way, it's a domain where we can escape that evolution trap of just trying to make things a little bit better. And it's a place where we can make things really be engineering. And let's briefly review a few of the central theoretical concepts. So, what's the basic idea of like literally all of machine learning? Well, similar data points have similar labels. Like that is the boring, sad property of virtually all of machine learning.
No, boring, happy property.
Boring, happy property. No, like in a way, there's very much not magic behind machine learning. This idea, similar data points have similar labels, is what it's about. And now we can be a little more precise about it. But like kernel-based machine learning, I think I mentioned it last week, for a while in the early 2000s, everyone was using it because it was working better than the others. In particular, because we had small data sets of them. Who of you knows what's the time complexity of support vector machines? This would be so much more fun if we were all sitting in the same room. Okay, Namita wins the golden emoji crown here. N to the 3. Indeed, support vector machines require a matrix inversion where the n to the 3 is coming from. So basically, support vector machines become crazy bad as the number of support vectors goes up. And of course, this is great if we're in the domain where we have thousands of them. 10 to the 9 is still a perfectly fine number for like even not so modern processors. It's of course not so cool if we have like 10 to the 8 samples, as we currently often have. So what if we instead look at neural networks? You know, like, what's the time complexity of neural networks? Well, there's going to be, if we have n samples, I need to show each of the samples to the neural networks. There's no doubt. What else is making neural networks slow? Well, every weight, where m is the number of parameters, every one of them generally means I need a multiplication on the way forward, and I need a multiplication on the way backwards. So therefore, it's dominated by this term O of n times n. And then there's extra factors that depend on the complexity of the problem and the spectrum of the singular values, and so on and so forth. But basically, neural networks, therefore, as we go to that domain of very large n, are very strongly preferable to support vector machines, which is arguably one of the reasons why they basically won. Because in the end, we came up with ways of producing really large data sets. Why? I mean, like, the data sets, of course, co-evolved in the end with neural networks. You know, like, neural networks benefit a lot from larger data sets. Therefore, there's an interest for Google and others to basically collate all the data that they can possibly find in one data set. Then we use these data transformations. You know, like, we flip things, rotate things, we crop things, we do all those things to have even more data. Why do we do that? Because basically increasing n in the time complexity of neural networks is like totally harmless. So deep learning also a kernel machine? And it turns out that it is. And there is a set of beautiful papers called Neural Tangent Kernel. And we might get into it later on in the course. But the important thing is that you can basically show that a neural network, if it's big under certain initialization assumptions, works just like a kernel machine, where you can say, what I want is that every sample that I have every sample X that I have has a certain influence on the sample, on another sample X prime. And I can characterize that by a kernel. And so for a specific set of kernels, namely those characterizing neural networks, we can basically do the same thing that we would get with n to the 3 cost with n times m cost. So in that sense, we can play in that same space, but it's computationally much cheaper. Lyle.
So Conrad, can I interrupt? Because I remember way back some early cool theory that contrasted starting with a fixed set of kernels. You start in advance and say, I'm going to use whatever kernels, Gaussian, sinusoidal, but say Gaussian kernels, versus a world where you had adaptive kernels and you could fit and reshape and resize the kernels to fit the data. And the claim of these theorists was that if you could have adaptive kernels, you could be vastly more efficient because you could put the kernels where you need them rather than having kernels everywhere. Is that still believed to be the case, or is that sort of ancient lore?
No, that is what feature learning is. Not like so neural networks arguably do two different things, and it turns out that it's well understood the axis on which it does. It's one of them is called the rich regime, and the other one is called the kernel regime. So if you initialize it with large weights, neural networks, it works like it's purely in the kernel regime. And if you initialize it with small weights, you have what's called feature learning. Now, and Lyle's exactly right. Here is like, let's go back to that definition. Similar data points. There is a slight question like, what does it mean, similar data points? And Lyle says, well, we should learn kernels. Yes, we should learn kernels. What does it mean to learn kernels? We want to figure out which data points are more similar. And you can say, for example, when it comes to vision, data points where it's the same object, but it's moved in space, should be more similar than data points that are just more similar in raw pixel space. And that is exactly the goal of feature learning. So if we go here to feature learning, you can say what we expect neural networks to do. Now, like feature learning was a strong driver to neural networks with the idea that we want sort of the early areas, early parts of the neural network to figure out those dimensions matter. They really, if this dimension is different, then they're really probably very different things. And these things don't matter so much. So the idea is that metric, that kernel that we'd be using here, that is something that we want to learn. And in fact, if we go back to the support vector machines, this is something that the field was very much interested in learning, and learning with kernel was a very, very big issue back then. And indeed, you want to build in things like, for example, translation invariants, and people were building that into the filters. With many different ideas, like virtual support vectors were one of the tricks. Great, and in any case, so yes, what Lal said, of course, completely spot on. We want to make the kernels be good, and today, this week, we will see some of these examples from the rich regime. So if you look at the results of Ganguly and Andrew Sachs, it's an example of what happens in that rich regime. It effectively regularizes things. It effectively figures that there's some dimensions that are really important that we should put a lot of stock into, and then there's other dimensions that are much less important. And you will see how that already emerges in deep linear networks. And the reason why it emerges is very intuitive. Now, you can say there's dimensions that carry variance that are important, and we want them. and we will learn them quickly, and you'll see why we will learn them quickly. And then there's dimensions that are just less important, and figuring that out, what the important dimensions are, implicitly means that you learn a better metric, that you get better at figuring out which things are similar and which things are dissimilar. Cool. But again, like a lot of theory and deep learning, the things that make it work is that you have many aspects. Like there is the kernel-based way of thinking, that and neural networks are a little like that. And then there's the learning the important features things, and neural networks are a little like that. And the reason why we want our parameters so tightly tuned is because we are navigating this, how much do we want to learn what the features are versus how much do we want to be close to like the similarity notion. And they're both all happening at the same time. Cool, so let me skip over these. And let me just very briefly touch on the no free lunch theorem. So the no free lunch theorem says that if an algorithm performs better than random search on some class of problems, then it must perform worse than random search on the remaining problems. And it's true for any pair of algorithms. Any algorithm that outperforms another algorithm on what you're doing will do worse than another algorithm on things that you're not doing, hopefully. And that's a little bizarre. It means that the only reason why we can be good at something is by specializing. And it should end this craziness that people have, that they say like, yeah, what's the best learning algorithm? Like the best learning algorithm is the one that is really good at what, no, you can say the best learning algorithm for your problem is the learning algorithm that's really bad at all other problems. You want that the learning algorithm basically contains relevant information about your problem. Now, like in other words here, a superior black box optimization strategy is impossible. If our feature space is unstructured, we can do no better than random. Like if there's no structure to discover, you will be random. A jack of all trades is a must have none. And that goes back to Walbert and McCready, 97. I should also say there's much older research by that's called the arbitrarily slow convergence theorem that basically makes those same points already. That goes back to 84, I believe, by Devroy. In any case, algorithms only work because we put in things. And so, for example, let me give you an example. Imagine we are in a world that looks like our world, and we want to find the high points on this planet. A great way of doing it is just walk up. You are dropped off from a plane, you just walk up, and you have a good chance to eventually discover Mount Everest. But I can construct a different world where, namely, where on top of the highest mountains, like there's a big hole that goes all the way to the bottom, and at the big minima in this world, there's just like a really high pole at that place. And in which case, the algorithm that I just described, which is walking up, is exactly the worst algorithm. You should walk down, because right where you walked all the way down is the highest possible point. Here's the Devroy on arbitrary slow rates of global convergence and density estimation. Wonderful paper. Now, I'm kind of out of time, but I just want to highlight the highlight from my perspective conceptually about like this week 2. So week 2 does 2 things for you. The first thing is it gets you closer to the whole mechanism of designing neural networks, which is great and important. The other one is it's really a jump off point to start thinking much more about the theory of deep neural networks. And so there's 2 papers that I want to mention. The first one is Understanding Deep Learning Still Requires Rethinking Generalization. It's a paper with Ben Recht and Oriol Vinyas, who basically pointed out that with traditional ways, they pointed out 4 years ago or so, that with traditional ways of thinking about generalization, neural networks make no sense. Not like lots of parameters, in fact, far more parameters than they have, than they obtain training samples. So in theory, neural networks should never work. And neural networks don't know about that and work just fine. And in that paper here, so they recap what they did 4 years ago. and they highlight in that last section the new developments. And it turns out that there exist new developments that have non-vacuous bound. That's basically say, if I train the data, my algorithm on some data, here's the mathematical reason why on new data neural networks will actually work. And you can give bounds on that, and those bounds are no longer perfectly pointless. There's a new development called pack-based for deep learning, which is where many of these new non-vacuous bounds are found. And I should mention here, there's some great work by Gintara Tsugaite of Toronto and Dan Roy. And there's reasons, and the field has also figured out a lot of reasons for implicit regularization. Basically, how do neural networks figure out what they converge to? And I should here, like, is the paper by Gintara on the role of data in pack bounds, where she shows that where they talk about pack bounds, pack base uses priors, and how it makes how you can make this approach be more data dependent, and how this often makes a huge difference between a proof that is perfectly pointless, where you can prove that it will not be much worse than chance, to a proof where you can say, yeah, like this should actually work on your data. And so it sometimes makes a big difference. And I want to, as part of this in-person lectures, always just highlight a paper or two that is recent that I found fun. And that's it for today.
One meta point. So we will post readings to these papers. These are supplemental. Some of you will want to go into depth on some of these and read them. The core learning is the material in the worksheets. And the goal here is to give a little peek at some of the cool thing that's happening on the contemporary research. They're optional.
Yeah, and it's absolutely not mandatory. I don't expect any of you to read these papers in preparation for class, but I want you to also see that you're surrounded by a set of like super cool papers that really have deep intuitions. And for some of you, this will be great fun. So what are the to-dos for this week? Anka, do you want to go through them?
I think we already did at the beginning. Okay. You had the same slide, I think.
Again.
Cool. Okay, this is just a reminder. Pod start, submit your workbox by Monday. And I should also say, if anyone has individual questions, I will stay on this channel for a little longer, and you should feel free to ask any questions. And thank you for everyone to be here, for being here, and for the answers of some of the questions.
Thank you. Have a great week.
Conrad, I had a slight confusion question for earlier on the presentation.
Cool.
So you were talking about kind of, I guess, redefining the search space when you were talking about constraints with the like size versus body size versus a heart size, that kind of thing. And I might have misunderstood, but from what I thought was said, it's like you choose one parameter that kind of evolves as you're doing the deep learning, and then you, based on how that parameter evolves, the other parameters are tied to that evolving parameter, and that's how you redefine the whole search space. Is that correct?
Yes, exactly. So look, let's just contrast two cases. Now, like in one case, you design your neural network and you choose your learning rate and you run it, and it might not work so well. Then you try with the bigger learning rate and the smaller learning rate, and you basically optimize it like that. Whereas if you go to development, you basically take your neural network with an unknown parameter, which is learning rate, and then you throw it at a hyperparameter optimizer, where you basically say, well, now try all learning rates until you get the fastest, the learning rate that works best for this, and I'll come back tomorrow and we'll go from there. So in the first case, you set both parameters. In the development case, the hyperparameter optimizer solves it. In the deconstraint case, you can say that it's rather that I say, oh, in general, like based on lots of experience with similar problems, neural networks with more parameters like are better off with lower learning rate, where you can say, well, and the learning rate by default is then basically like a little smaller if there's more parameters or something.
Okay, I see. Then in the development case where the hyperparameter kind of sets a lot of the other parameters, it seems like there's going to be dependence of the parameters on each other. And so we're introducing parameter dependence. And I'm wondering if that ever causes an issue, because in the example you gave, which is very intuitive for me as a bioengineer, but like body size and heart rate, or like heart size, I could easily see why there would be a dependence with each other, but that's not always something that we know going into the different problems that we have. So is there ever a scenario where we have to worry or like, think carefully about that?
Yes, there is. No, like we don't know the shape of the meta optimization function. Mm-hmm. Like you can say, what we do is we build networks and they have like structures and anatomy and like dependencies and so forth. And we don't know how the parameters there relate to one another. But you can say, just like in the rest of machine learning, we will assume that things are smooth and that similar. No, we implicitly assume that similar networks do similar things. And then we try to learn on top of that. And if there's a lack of structure, that will fail in the same way as our neural networks will fail one level lower. But no, like that's the slight problem. We don't have a meta theory. If we had a meta theory, if you could say, if we would understand how the neural network depends on its parameters, and that's why it's so important to try and understand it, then we could say we solve it for good. And when it comes to say network initialization, that has happened. So we now use Hay and Xavier initialization. And the reason why we do is because we now have an understanding of the various goals of initialization.
Yes, sir. Okay, great. Thank you.
Cool. Any other questions? So is anyone still here who wants to ask a smaller question, or like a question or a group question or something? Okay, well, if no, just let me know in chat if anyone wants to say talk in person or something. But otherwise, thanks so much for being here. And
did a question in chat? Can you please check that?
Question in chat. Okay, cool. Yes. So I have a question by Sian relating the previous questions on subject recognized cross-validation. I'm not sure I fully understand that. The following is my understanding. For predicting tweets from the same group of people, we will want to use record-wise. And for predicting tweets from new people, we would want to use subject-wise cross-validation. Is that correct? Yes. So if you have a data set where you want to be really good at predicting what Conrad means, and let's say you do a long time varying study on Conrad, where you basically, Conrad, how you feel today, and then you download my tweets and you do that tomorrow and so forth. And for some reason, it would be really important for you to be good at predicting how Conrad feels right now. Then record-wise cross-validation is perfectly good. Like I want to predict the same subject at a later point of time, and I'm fine of using other subjects if it helps me. But this is not usually the setting of machine learning. Like what we usually do in machine learning is we produce a data set to be good at answering a given question, and then we want to roll out the software that we thereby produced and like use it more broadly. And that setting, of course, then asks for a subject-wise cross-validation, because we want to know, once I productize it, can I now, so take an example, let's say Google Flu, like they were trying to use my search queries to find out how the flu moves through America. It was a complete disaster. It worked great on their past data. It never worked again. But the idea there is what do we want? We can take data from a couple of subjects where we say like, okay, do you actually have the flu? push the button. Do you have the flu? Yes, no. Or like, here's medical data that says that's the flu or not. What we want is that generalization of like, now can I also help other people with it? So therefore, for almost all real world scenarios that I can think of, you want to do subject-wise cross-validation. But let me give you another example. Let's say we all carry, a lot of people carry Fitbits with one another. You can say it's perfectly legitimate to use record-wise cross-validation there, because people feed it with like their own label data for a long period of time. So you can say, well, once I label 100 days, if I feel good or bad, this looks more like a record-wise cross-validation problem where I want to use my past. But in that case, it's not record-wise. No, it's like time forward-wise cross-validation, where I want to say, can I predict how I feel on day K based on K-1 up to 1 previous days? In which case, the cross-validation structure should take that into account, because if it doesn't, if I randomly sample, I'll be wrong, because say in temporal data, I only get older. So we need to basically predict what will happen in the future based on what happened earlier. So it's not as simple as randomly sampling. And so you can say time forward cross-validation, where like you always make predictions based on the first K samples of the next whatever, how many samples. Great questions, though. And those are the subtle things, and those are the mistakes that sink companies and that sink research projects. That basically people get the logic wrong that they have to evaluate if their machine learning algorithms are useful, and then things go really wrong. Cool. Any other questions? Okay, so if there's, oh, hold on, one more message. Oh, thank you. Okay, cool. Okay, if there's no more questions, thanks everyone for being here. And I look forward to seeing you next week.